doing today is we're going to talk about bow tie diagrams. We're going to talk about, actually, let me do this. So basically what you're looking at here is bow tie Q. Now, bow tie Q isn't available yet. Technically, if you really want it, you could sweet talk me into it, but it's Connexus's tool for performing bow tie analysis, which is linked to our OpenPHA tool for doing HAZOP-LOPA. So we make life really easy if you want to take scenarios out of your HAZOP and display them as a bow tie diagram and then integrate them and such. But we will be having, keep your eyes posted, because we will be having a very big launch event scheduled for the end of January, I believe, where we will be doing a product launch and we will be launching all kinds of education. So those of you that are familiar with bow ties are probably used to seeing something that looks like this. So you've got threats on the left-hand side, or causes or initiating events. Whew. Boy, that's one of my lifelong missions, is something that I refer to as unified hazard assessment. Because why do we have to have a different name for the same thing depending on what tool we're using? So yes, it's a threat, it's an initiating event, it's a cause, initiator, whatever you want to call it. And then we have safeguards. Well, we call them safeguards in a HAZOP. We'll call them IPLs in a LOPA. But in a bow tie diagram, we're going to call them barriers. These are things that will prevent your threat from turning into a hazard. So a hazard is the knot in the bow tie, where generally in the chemical process industries, your bow tie knot is going to be the loss of containment. And there are multiple different causes or ways, threats, ways that you could get to that loss of containment. And for each one of those threat, there will be zero or more preventive barriers. And what a preventive barrier is, and the preventive barriers are on the left side, they're associated with an individual threat. They are going to prevent that threat from causing a realization of the hazard or causing a loss of containment. Now, when the hazard occurs, there's a potential for many different outcomes. So in this case, I'm overfilling a storage tank, and the consequence could be a huge unconfined release if the dike fails, or it could be a small release if the dike works. And I'm either going to ignite the material or not ignite the material, which is why you see 4 different consequences here. Now, most of the time, to this day, the bow tie diagrams are done exactly as you see here, in terms of they're just a pretty picture to describe the scenario. So basically you're just drawing a hazard scenario in a format that's visually appealing and it's easier for visual learners to understand. Well, what we're doing with bow tie Q, the Q in bow tie Q is quantitative. So what we're doing is we're actually going to go ahead and put some numbers on there to where we can calculate things. So we're going to have frequencies for initiating events. We're going to have PFDs associated with preventive safeguards. We're going to have probabilities associated with mitigative safeguards. And then we're going to be able to calculate frequencies of consequences and compare them against target maximum event likelihoods to determine whether or not the risk of that particular consequence is going to be tolerable. And what you're going to see when I get into the details of the discussion is that we're basically applying the same math for the same reason as we would in layer of protection analysis. The difference is layer of protection analysis only has one outcome. But with the quantitative bow tie in the same structure, we can handle multiple different outcomes and determine the tolerability of each of those individual outcomes separately. So that's where we're headed in the discussion today. Where are we going to, or what are we going to use as the basis of our discussion? We're going to use the upcoming Connexus bow tie analysis theory and fundamentals training class. This course has not been released yet. It will be released on that official release date coming up in January. So sign up for the Connexus newsletter, if you want to get these kinds of announcements on when these training classes and products are launching. So in the bow tie analysis training class, we do a deep dive into all aspects of bow tie analysis. But the group that I have here today, I'm going to assume you know what a bow tie is for the most part. You're going to understand what threats are, what barriers are, and so on. And what we're going to focus on today is, instead of the nomenclature or building the bow tie, we're going to turn it up a notch and we're going to say, okay, I have a bow tie diagram and it's completely a qualitative description. Now I want to put numbers into it. And that's going to be section 3 of our bow tie training class, entitled Quantitative Bowtie Analysis. So section 3 is what you're going to get today. Section 3 out of 9 sections total. That full training class will be coming up later. And keep your eye out on the announcements. This is going to get launched through the Connexus Process Safety Training Center, which is our learning management system that's built into our KISS, Connexus Integrated Safety Suite platform. And when we first launch this, we're going to give away free 3-month licenses to the Connexus Process Safety Training Center so that you could take this training class for free, and all you need to do is follow us in LinkedIn. So keep your eye open for that. So what we're talking about here in quantitative bow tie analysis is we're going to enhance a traditional bow tie diagram by actually putting numbers on it to calculate the frequency of consequences ultimately, so that we can compare them against tolerable frequencies. We're going to explain how we move from qualitative to quantitative, and we're going to have a little bit of a discussion of why you want to quantify risks. Well, ultimately, if you don't put numbers on things, everything is just gut feel, which makes it not repeatable. And different groups will get different answers. So when you put numbers on things, it makes it easier to gain consensus and consistency. We're going to talk about probability and frequency data. Where is that data going to come from? Well, little secret, the same place that you got it when you were doing your LOPA is where you're going to get it from in quantitative bow tie analysis. And then we'll close out with some of the benefits of doing quantitative bow tie analysis in comparison to traditional bow tie, and then also in comparison to HAZOP and LOPA. Okay, so let's start out with kind of the basics. Risk metrics, risk tools that we're going to use when we're doing a quantitative bow tie. In bow tie analysis, we are going to be utilizing frequencies and probabilities. Ultimately, we are going to calculate the frequency at which we expect a consequence event to occur. That frequency can be compared against a tolerable frequency for that degree of hazard. And I lost my R right there. So I was editing the slide right before we started and I clicked the delete button too many times. Okay, what is frequency? The frequency is the number of occurrences of a specific event over time. So how often does something happen? How many instances over what time duration? Probability, on the other hand, is the likelihood that an event will occur given a certain set of circumstances. Probability is going to be a number between 0 and 1, where the probability of 0 means that that event will never happen, and the probability of 1 means it will always happen. Probability is dimensionless, as opposed to frequency, which is going to carry inverse time units. So a probability is going to be associated with a certain situation, a certain event, or a certain time frame, whereas frequency is going to be dependent on the time variable. So depending on what time units you're going to be using, things can change. So frequency and probability are the two metrics that we're going to be using that we're going to relate to risk. Now, we're also going to use logic in our bow tie diagrams. We're going to use and logic, and we're going to use or logic. So a logical and means the end result is true if all of the inputs are true. And when you have and logic, you use probability multiplication. Now, we say probability multiplication, but we're also going to be multiplying and adding frequencies. So I'm going to say probability multiplication and probability addition, but those same concepts are going to get applied to the frequencies too. So and, a logical and, we use probability multiplications, and that's when the events have to occur simultaneously together in order to get the outcome of interest. A logical or is when events are independent of each other but could lead to the outcome of interest. So I might get a low flow if my pump fails or if my control valve fails to the closed position. Those events are independent of each other, but either one of those events can cause a flow to go low. And when you have a logical or, you use probability addition. Now, if you want to go into more detail on probability addition, especially when related to failures, I will point you to the Connexus SIL verification training class that goes into all of the nuances of probability addition, because when all you do is add the numbers, the probability numbers together, you are overestimating the actual probability because you're ignoring the probability that two events will happen simultaneously. So in LOPA analysis, as in bow tie analysis, we're going to pretty much use a simplifying assumption that we call the rare event approximation. So if events are rare, the probabilities are small, let's say less than 0.1, then the effect of the simultaneous events becomes small. And as the probabilities become smaller, that effect becomes smaller and smaller. So if you want more information on the rare event approximation in probability addition, I encourage you to read my LOPA book that's available through ISA, and we also discuss it in detail in the SIL verification training class. Okay, so yeah, we have logic in our bow tie, and we're going to use basic probability math. We're going to use probability addition for probability addition for ors, and probability multiplication for ands. And we're going to apply this type of math to the threats, to the barriers, to the outcomes, and also to that hazard event that's the knot in the bow tie. And I'll kind of walk through these items one at a time to make them clear. Ultimately, we're going to calculate the frequency of multiple outcomes, And we're going to determine whether or not the frequency of those outcomes are tolerable by comparing them against a target maximum event likelihood, or a TMEL. So that's out of Bowtie Q. That's kind of a sample of where we show you the risk tolerance criteria that you could build into a study. So for instance, in this case, if you have a single fatality event, this organization is only willing to tolerate that at a 1 in 10,000 chance per year, or a 1 times 10 to the minus 4 frequency. So the severity categories determine what frequency is tolerable for those types of events. Okay, they're associated. And what we're going to do is we're going to calculate the frequency of an outcome based on the threats and the barriers. And ultimately, what we're trying to determine is, do I have enough barriers, and do those barriers have enough integrity to make all of the potential outcomes that are possible in my Bowtie diagram tolerable? Okay, so where do you get data from? The failure data is very important because it's going to determine the frequency of my initiating events, or my causes, or my threats, whatever you want to call them. And it's also going to tell me what the probability of failure of my barriers, or my safeguards, or my protection layers is going to be. There are a lot of sources of failure rate data. There's going to be industry databases from ORIDA's offshore reliability data, NPRD from the Reliability Analysis Center, CCPS, and Connexus. So Connexus has libraries of probabilities of failure, of safeguards, and initiating frequencies for initiating events. But the most common resource is going to be the CCPS IPL book, which gives, or IE and IPL book, so initiating event and independent protection layer book, which discusses common IPLs, common initiating events, and rationalizes a reasonable number to use. So we're going to use this information to assign frequencies to threats, and then we're also going to assign probabilities of failure to protection layers. And sometimes we need to calculate those probabilities of failure based on the equipment that's being used and how often they're being tested, and so on. Okay, so let's start out by looking at probability addition, or frequency addition, in Bowtie analysis. So in Bowtie analysis, the starting point is knowing what the hazard is that they're trying to prevent. So as I'm going through this first example, I'm going to move away from the process industries and go into something a little more general purpose. And that would be a data center. So if I have a data center, it relies on electricity being available to run all the computers in the data center. So if I have a loss of power to the data center, that's bad. That's something I want to avoid. So I'm going to want to look at safeguarding my data center against loss of power. So once I know that loss of power is a hazard that I'm concerned about, the first thing I'm going to do to build this up is to determine, well, what could cause a loss of power? What are the threats or initiating events or causes of loss of power? So in this case, I determined that, okay, well, if the electrical grid fails to supply me electricity, well, that's going to cause me to lose power. But I also have transformers and switchgear inside my data center, and if that equipment fails, I'm also going to lose power. Now, item number 3 is just straight up human failure. So an operator might switch the wrong switch or do other activities that cause the power to fail. So those are 3 threats that I identified. So as you can see, a hazard can be caused by multiple things, multiple initiators, multiple causes, and they are logically related as an OR. So I will lose power if there is a grid failure, or if there is an equipment failure, or if there is a human failure. These are all independent of each other, and any one of them by itself can cause a loss of power. When you have a logical OR, you do probability addition. So you'll see the frequency here, and we'll come back to this. If I said that the frequency is 5e minus 2 for grid failure, 2e minus 2 for equipment failure, 1e minus 2 for human failure, then a logical OR will do probability addition. So 5 plus 2 plus 1 gives me 8 is the frequency of the power failure. Now, limitations on probability addition in general, specifically when you're doing it at bow tie. Independence is critical. What I've assumed when I do this probability addition is that all these causes are truly physically and functionally independent of each other. If they are not independent, so if there's common equipment between the grid and my internal equipment, that common equipment can cause both of the routes of failure to happen at the same time. So interdependence between events are going to require other methods of analysis, which basically the bottom line there is if you have interdependency, you're going to want to switch to fault tree analysis and use Connexus's Arbor fault tree analysis tool. You like that? Got to put that little trademark on there. Anyway, okay. So speaking of Arbor fault tree analysis, you'll see that the math that's happening between a bow tie diagram and a fault tree analysis is exactly the same at its simplest level. So you can redraw this same exact situation that I drew up here as a fault tree. So our top event, or the loss of containment, the hazard, is loss of power to the data center, and then each one of the threats is a basic event, and then you assign frequencies to the basic events, put everything under an OR gate. You know, it's an OR gate by the shape. So the OR gate means we're going to add all of the frequencies of the initiating event, and you get 8 times 10 to the minus 2. So you get exactly the same number. Okay, so it just kind of goes to show you that there are a lot of different ways to perform the same task, and ultimately they should come up with the same answer if you do them correctly. Okay, probability multiplication is an AND gate. So I'm going to use probability multiplication when multiple things need to be true for the outcome to be true. So in this case, I'm looking at and down here at the bottom is where you see my quantitative bow tie. So in order for loss of primary power to occur, to result in loss of power to the data center, and loss of primary power, that's this grid failure here. So I probably should have called it grid failure over there to avoid any confusion. So if I have a loss of primary power, that doesn't necessarily mean that I will have loss of power to the data center, because I have barriers that can prevent the hazard even though the cause has occurred. And in this case, I've got a couple of barriers. So I have a backup generator that when I lose my primary power, the backup generator will turn on and supply power to the data center. I might, well, in this case, I do also have uninterruptible power supplies that will immediately kick on and supply power to the data center. So in order for me to lose power to my data center, I will have to have a loss of primary power and a loss of the backup generator and a loss of the uninterruptible power supply. When you have a logical and, you do probability multiplication. So in the case of the probability of failure of your barriers, it's a logical and you're going to use probability multiplication of the probability of failure of the barriers to get to the point where all of the barriers fail. So in order for all of the barriers against loss of primary power to fail, my backup generator would have to fail, and because we have a straight line down at the bottom, and the uninterruptible power supply would need to fail. So the probability of the backup generator failing is 0.01. The UPS failing is 0.05. And when we multiply those together, 1e minus 2 times 5e minus 2 gives me 5e minus 4. So looking at that in the quantitative bowtie down at the bottom, the whole string from initiating event through the barriers to the hazard is going to be a probability multiplication because it's a logical and. I will lose power to the data center if I have a loss of power and my backup generator fails and my uninterruptible power supply fails. So I'm going to multiply 1 times 1e minus 2 times 5e minus 2, and that's going to get me 5e minus 4. So that's how we're going to deal with the probability of failure of barriers, preventive barriers, in relation to the initiating event that they're associated with. Okay, so now continuing on from where we were on the slide previous, when you're calculating the overall threat frequency, you're going to multiply the frequency of the threat by the probability of failure of all of the preventive barriers that are going to be in between the threat and that hazard, that loss of containment event, or that situation where the hazard is realized, always using probability multiplication. So another example here, if my primary power is lost due to grid failure and my uninterruptible power supply fails, you multiply 1e minus 1 by 1e minus 1 is going to give you 1e minus 2. Continuing on, so now we've calculated the frequency, or we know we went through the mechanism of calculating the frequency for each individual threat, considering its preventive barriers. So on the last two slides, we showed how you get to these numbers. But a top event is going to have multiple threats. There are multiple different causes or multiple different pathways to get to the top event. And how we're going to combine their probabilities, or frequencies technically in this case, is through probability addition. And this is actually kind of going back to where we started. So I want to know the frequency of loss of power to the data center because of grid failure. I calculated it at 1e minus 2. I want to know the frequency of loss of power to the data center because of internal equipment failure. I calculated it 2e minus 2. Logically speaking, loss of power to the data center will occur if either primary power is lost or if failure of internal equipment happened. Because it's a logical or, you're going to use your probability addition. So 1e minus 2 plus 2e minus 2 gives me 3e minus 2, and that's how we calculated the frequency of the top event. But alas, just because we know the frequency of the top event, we are not done. Because we don't really, well, not that we don't care, the top event frequency is not the same as the frequency of the consequence. And it's the consequence that we're actually concerned about. And each top event can have multiple different consequences associated with it, and those consequences can have different tolerabilities of risk because they have different magnitudes or impact different assets. So what we need to do next is we need to then calculate the frequency of a consequence. So for this case, I'm starting to switch over to my other example, which is a process industry example. Overfilling a tank is different from an uncontained spill that has caught or that did not catch on fire and has a significant environmental consequence. So I had an overfill, that's bad, but the consequence that I'm concerned about is the uncontained spill, failure of secondary containment, so the diking didn't work, and I had a very large spill with a significant environmental consequence. Now, I put a target maximum event likelihood of 1e minus 2 on that. Let's put a pin in that. We're going to come back to it a few slides from now to understand where that came from and how I'm going to use it. So this item here is what I want to avoid, and that is the number I need to calculate a frequency for. How do we do that? Well, we know what the frequency of the loss of containment event is. We know the frequency of the hazard, the knot in the bow tie. That's the starting point for determining the frequency of the consequence, because there are going to be barriers on the right-hand side of the bow tie diagram that represent mitigative measures. So a mitigative barrier is something that doesn't prevent a loss of containment, but it makes the consequences of the loss of containment smaller. So if I have an overfill of the storage tank, I will have an uncontained spill if the dike fails. So if my secondary containment system fails, then my overfill will result in a large uncontained spill. And I need to go ahead then and put a probability of failure on demand on this mitigative protection layer, the same as I did for the preventive protection layers. So the frequency of the consequence, we're again going back to probability multiplication, because in order to get an uncontained spill, I have to have a spill, that's my bow tie knot, and I need my containment to fail. When you have a logical and you do probability multiplication, well, in this case technically it's frequency multiplication. So I'm going to multiply 5e minus 2 by 1e minus 2, and then I would keep multiplying by the probability of any other mitigative barrier, And the end result gets shown in Bowtie Q. The end result gets shown here for the frequency of this consequence. So right now, we've calculated the frequency of the uncontained spill consequence is going to be 5e minus 4. Now, you'll notice the little green light here. Where did the green light come from? Well, this means when you see the green light, the risk of the scenario is tolerable, or the risk of that outcome is tolerable, because the maximum is 1e minus 2. My estimated calculation was 5e minus 4. The estimation is less than the tolerable, so tolerable risk has been met. How do we do this? How do we know this? Well, you can manage the risk in your bow tie with TMEL criteria. You can also manage risk using matrices. Most people are using TMEL criteria, which is what you're seeing in these quantitative bow tie examples. So there are multiple different ways to represent risk, and the TMEL tables and the risk matrices are ubiquitous in the process industries. So we're going to define a category for our consequence, and then either we're going to calculate the frequency of that consequence, or we're going to put criteria on the likelihood and put them into bits. Yes, Chris, I assume we have a question.
We do. How do you deal with the fact that different threats lead to different magnitude? Which frequency do you take?
Very good question, and I will get into that when we get into the example. So bear with me a few seconds. Ultimately, this comparison of tolerable risk against frequency needs to happen not one time, but for every outcome that is possible. And I'm going to show you that when we get into the example of the overfill. So sit tight, I'm getting there. Okay, so risk matrices, they form a very good visualization tool. TMEL it has a little bit more horsepower for when we're doing our quantitative analyses, because it gives us that target number that we're going to compare our consequence frequency to. And it's important to remember that this consequence category that you pick, you're going to do it not once for the scenario as a whole, but once for every outcome that's possible as a result of the more complex scenario. Okay, now, when we do our analysis, there's another benefit of what we're doing is sensitivity analysis. So when you're performing this quantitative bow tie study, you have the ability to take barriers out or change the effectiveness of barriers and see how the risk profile changes and whether or not risk is tolerable. So if you put a safeguard into bypass, that converts its probability of failure to 1. How does that impact the full range of outcomes that are possible? This sensitivity analysis is also going to allow you to identify the critical barriers. So the more threats that a single barrier is associated with, the higher the impact it's going to have on the output criteria. Sensitivity analysis is also going to include allowing you to test variations in barrier effectiveness. Do I need a SIL 1? Can I get away with basic process control system? Maybe SIL 3 is required. So changing the different effectiveness to allow you to make decisions about your testing frequencies. You can also look at, ultimately, what is the consequence frequency that is going to happen when I change my inputs? So as you change your inputs of threat frequency and barrier effectiveness, what impact does that have on the consequences, and what does that mean to the overall risk of the plan? Ultimately, this type of tool is going to allow for a more informed decision making than if we only show the words, if we only do it qualitatively. This is going to allow us to focus on the barriers that have the greatest impact in risk reduction when we're designing our maintenance programs. Okay, so let's do a case study. When I did the example above, I started in a data center, and then I kind of started to move over to this overfill. But I'm going to flesh out this diesel tank overfill scenario in a lot more detail. And I'm going to build up the bow tie diagram. I'm going to quantify the diagram, and then we're going to talk about the risk decision making process, whether or not tolerable risk has been achieved. So this is our plant right here. Well, actually, we do have a diked area around this diesel fuel tank. Well, you know, this is what happens when you get stock footage. They probably should have had a secondary containment. But here we have our diesel storage tank. We're going to run a bow tie diagram to look at its design and the design of its associated barriers. The first thing that you're going to do is, well, actually, the first thing you're going to do is you're going to start with a top event. So the hazard that we want to protect against, we know that if we overfill this storage tank, that's going to be bad. So step one, tell me all of the causes of overfill of this storage tank. Now, when you're doing this, you might go back to a layer of protection analysis. You might go back to a PHA like a HAZOP study, or there's no reason that you can't start your analysis actually in the bow tie paradigm. So in this particular case, we have a level controller, and if the level controller fails, it can result in an overfill of the storage tank. And for this particular storage tank, we're receiving diesel from a pipeline. So the paradigm is when the level goes low, operations will request that the tank be filled from a pipeline. The operations group will enter a volume of material that they would want put into the tank and hit start, and the controller will open a valve and meter in the amount of material that they need to fill the tank. Once they've received that totalized flow of diesel fuel, it'll stop. So if the controller fails, you're going to overfill the tank. Also, if the operator requests more material than the tank has capacity to store, you will also result in an overfill. These two initiating events are independent of each other, or we're going to assume they're independent of each other. They wouldn't be independent of each other, for instance, if the operator requesting the transfer is using the same level measurement as the controller. There, a failure of the controller indicating an erroneous level will cause basically both of these things to happen simultaneously. At that point in time, you need to go into fault tree analysis. And guess what? I've already done a webinar on doing that fault tree analysis. So go back to the Connexus website and you can find that webinar in doing this kind of scenario in a fault tree if you're interested. Okay, so for each one of these initiating events or threats, you're going to need to quantify it. So in open bow tie, let me jump out of here for a second. And so if you go into open bow tie, excuse me, if you want to add a new event or add a new cause, threat, you just click here and you're going to add a new cause, and then when you double click on it, you're going to get the full range of things that you can quantify. So you can title the cause, name the cause, put frequencies on, and so forth. So that's how you would add it. I'm going to delete that because we've already fleshed things out. So in terms of the failure of the tank level controller, these are the attributes that was assigned. So I've got two causes, and both of them have a frequency of 1e minus 1. So if you go back to the CCPS initiating event and independent protection layer book, failure of a BPCS system, 1 in 10 chance per year, is a number that they recommend. And when you're looking at the frequency of a human failure, you need to multiply the probability that the person gets the task wrong by the frequency at which they're asked to do it. So for instance, in this case, if an operator has a 1 in 1,000 chance of typing in the wrong number, and you multiply that by 100 times per year they're going to type in a number, you end up at 1 in 10 chance per year. So a lot more information on that concept, if you're interested, is going to be available in the Connexus LOPA training class in our Process Safety Training Center. Okay, once we know what all the causes are, we're going to look at the preventive barriers. And the preventive barrier is what you typically think of when you're doing a LOPA. What are the things that, if they are successful, they will prevent the consequence from occurring wholesale? They will stop the scenario in its path, and you will not have that loss of containment. So the preventive barriers in this particular study include a high-level interlock that is going to detect that the level is high and close a separate valve, separate from the basic process control system valve. Also, we have operator intervention based on high-level alarm that will allow an operator to go out and manually close a manual valve that's separate. So independence is going to be important here, exactly the same way that it is important in a layer of protection analysis. So in this case, our high-level interlock is a SIL2 with a PFD of 1 times 10 to the minus 2. And our operator intervention, we gave it a PFD of 0.1, again, consistent with the guidance you'll see in the Connexus handbooks and also in the CCPS handbooks. Now, this barrier is used in multiple locations. So let me kind of jump out of here for a second. So when I modify a barrier, so you see level alarm 102, and I can expand the variables for these. This is not two separate instances. The way Bowtie Q works is it's on that relational database again. So if I go in here to level alarm 102, and I said, okay, well, I'm only going to get a 50% chance that this is going to work instead of a 90% chance that it's going to work, or converting that to failure. PFD of 0.1 might have been too optimistic, and we're going to say it's 0.5. When I make this change, it changed everywhere, not just that one instance. So when you define a safeguard, and I'm going to show you the safeguards here, there's only one instance of that safeguard in the database, but you're able to use it in multiple different locations. As you see here, all of these safeguards are used in 2 locations. Okay, let me go back to the bow tie diagram, and actually let me go back into the training class again. Okay, so that's how we defined the barriers. And then at this point in time, the software is going to automatically calculate, or if you're doing this manually, you can manually calculate the frequency associated with each cause or each threat. Same math as LOPA. Initiating event frequency multiplied by the PFD of the protection layers gives me the frequency at which the hazard will occur because of that initiating event, that threat, or that cause, whatever you want to call it. So once we've quantified the frequency of the hazard occurring as a result of each individual cause, we add them together to get the frequency of the top event. So a overfill of the diesel tank can occur because the BPCS failed or because the operator requested more material than the tank can hold, because it's illogical, or as we explained several times already, we do probability addition. So that overfill is going to occur at 2 times 10 to the minus 4, which is simple addition of the two events that can result in that top event occurring. Now, the next thing we're going to do is look at the consequences. So just because I have a diesel spill doesn't mean I'm going to get a multiple fatality event. It doesn't mean I'm going to get millions of dollars of EPA fines. So for this specific example, what we did was we looked at two different consequences. We looked at an unconfined release and we looked at a confined release. And this is a function, the number of outcomes that you're looking at is going to be a function of the number of mitigations that are possible. So if your only mitigation is whether or not the spill is contained, then you'll have one consequence if the spill is contained and another consequence if the spill is not contained. If another mitigation that you wanted to look at was probability of ignition, then now we're out to 4 different consequences. So unconfined ignited, unconfined unignited, confined unignited, confined ignited. I hope I went through all those exhaustively. So when you're looking at the number of consequences, you're looking at all the combinations, or is it permutations? Permutations of the mitigative barriers being effective or not being effective. So in this case, I only have the one mitigative barrier of the secondary containment, which means I have 2 outcomes. One is an unconfined release, one is a confined release. Once we define it in terms of terminology, now you need to put a consequence category on it. So jumping out again, and in this example, I have all of the 4 things built out, but I wanted to simplify it a little bit for the training class. So let's look at unconfined release with no ignition. So you'll title it, you'll give it a description, then you need to give it a consequence category. So we said this is a high severity. Where did that consequence category come from? That came from our risk tolerance criteria that you've already probably seen. And if you're a user of OpenPHA, you're going to say, wow, this is exactly the same stuff that I see when I'm in OpenPHA. So you have your matrices with all the different attributes of risk. You're going to have your likelihood table, and then you're going to have multiple consequence category tables, one for each attribute of risk. So when I went over and I define my consequence, you'll see that I only have the environmental listed here, and that's because that's all that I told it to care about. So if I go to the study settings, I can look at all of the different attributes of risk. So let me hit update. And when I do that, now you'll see that you have the ability to pick any different type of attribute that you're interested in. And you also then have the ability to pick its magnitude. So in this case, For the unconfined release of fire, we said the safety severity is very high, potential for multiple fatalities. Okay, so that's how those TMEL numbers get into the analysis. And also you see that they're different. So an unconfined release is going to be a huge spill, large cleanup costs, large regulatory fines, and we said that that is a high consequence. But even if you only spill your diesel fuel into your containment area, there's still a consequence. It's just that the consequence is smaller. So we said, okay, well, it's a small cleanup cost. There's no fines, maybe a minor fine, no damaged relations. So we're going to call that a low. And you'll see that the frequency that's acceptable for a high consequence is different from the frequency that's acceptable for a low consequence. So in this paradigm, in the quantitative Bowtie paradigm, you're not doing one outcome, you're doing every possible outcome and checking each one of them individually to determine whether or not tolerable risk has been achieved. So in this particular example, tolerable risk has been achieved for the confined risk, but it has not been achieved for the unconfined release. So we need to pump up our barriers in order to achieve tolerable risk. Okay, so first step is to list off all the potential consequences, assign consequence categories to them. The next thing that you're going to need to do is, for every one of those consequences, what were the mitigative barriers? So in this case, I have a mitigative barrier that says the dike fails. So the dike is going to fail at 1e minus 2. This number, again, that one came directly out of the CCPS book, the purple book, I believe. So if the probability that the dike fails is 0.01, then the probability that the dike succeeds needs to be the complement, or 1 minus that, or 0.99. Okay, so we're going to flesh out all of our mitigative barriers, remembering that the failure or success of a mitigative barrier are complementary to each other. And then finally, we're going to calculate the frequency. So I know that I'm going to get an overfill at 2e minus 4, but what is the frequency of an unconfined release? Well, in order to get an unconfined release, I have to have an overfill and my containment dike has to fail. So that's where your probability multiplication came into play. 2e minus 4 multiplied by 1e minus 2 gives me 2e minus 6. You do exactly the same math for the small confined release. So 2e minus 4 multiplied by 0.99 is going to give me 1.98e minus 4. Now we then do your comparison. 1e minus 4 is what is tolerable. 2e minus 6 is what was estimated. Green light. Risk is tolerable. And you need to repeat that analysis for every potential consequence that you can come up with. So in the early stages of a risk analysis of a project, it's very possible that one of these consequences is green lighted, but the other one is red lighted, and that's not okay. I need to make sure all the consequences are green lighted in order to make sure that risk as a whole is going to be tolerable. And that's kind of one of the primary benefits of quantitative Bowtie over LOPA, is that in LOPA you're really only looking at one of these consequences at a time, whereas in the quantitative Bowtie you're allowed to look at all, or you can look at all of them simultaneously, in addition to have a more visually appealing, easy to understand analysis. So interpreting the results, you need to understand the risk reduction that's provided by all of the barriers and what that risk reduction applies to. So preventive barriers may only address the risk associated with a single cause, and mitigative may only be associated with a single consequence, and mitigative barriers will have consequences whether they succeed or they fail. So you're going to have one consequence where the barrier succeeds and one consequence where the barrier fails, and you need to do your comparison against the TMEL of each of those consequences. This process allows you to identify the critical barriers. The more often a barrier shows up in your bow tie, the more critical it's going to be, and it's going to have a much more significant on the impact of reducing risk. So you know which barriers are going to be the most critical. That allows you to focus your limited resources on those barriers. You're also going to find areas of improvement. And how do you know that you have an area that needs improvement? A red light. You have a red light that needs to be green in order for your design to be tolerable. That's going to tell you if you need more barriers, and it's also going to tell you maybe you can improve your existing barriers to get their probability of failure on demand decreased. Ultimately, you're going to be able to make a final decision on the acceptability for the risk of the scenario as a whole, considering the multiple threats that are possible, the multiple outcomes that are possible, and all of the barriers, whether they prevent the loss of containment or they reduce or mitigate the consequences after the loss of containment has occurred. So that's quantitative bow tie analysis. Quantification, we talked about how we do the quantification of the threats, quantification of the threats after preventive barriers, quantification of the top events, and then quantification of the consequences considering the effectiveness of mitigative barriers. So talked about the difference between how preventive and mitigative are handled. We talked about risk metrics and how you use those risk metrics to then make decisions once we know the frequency of the consequences. We talked about probability addition and probability multiplication. Those are the two mathematical tools that are used in multiple different locations. Talked about sensitivity and how we look at that bow tie when it's complete, and we can change numbers around to see what's important. And then we finally talked about interpreting the results and making sure that tolerable risk is going to be achieved. So with that kind of talks or sums up the overall process of what we're doing in a quantitative bow tie. Before I turn it open to questions, one of the other benefits that you get in a quantitative bow tie diagram that you're not going to get in a layer of protection analysis is looking at the other attribute of bow ties that I haven't shown you yet, which is degradation mechanisms. So for a high-level interlock, I can click this button and it's going to show and hide the degradation mechanisms. So for instance, a high-level interlock will not work if it's in bypass. So all of the different mechanisms, and you can add as many degradation mechanisms as you want, or you can, sorry, that's not how I meant to do that. The degradation factors are handled elsewhere. Anyway, I digress. The different degradation mechanisms will then also have degradation controls. So I have bypasses, but I have a bypass management program that will prevent the bypasses from being used in the wrong way. So the degradation mechanisms is what you see here for bypass. Degradation controls is what you see for bypass management program. Right now in Bowtie Q, these are simply qualitative, and they're going to allow you to think real hard about all of your barriers. How can they fail, and what mechanical integrity features, policies, programs do I have in place to prevent those degradation mechanisms from occurring? So another quantum leap over a traditional LOPA. So what you're going to see, sorry about that, in the future is a lot of people that did LOPAs during the design phase in something like OpenPHA are going to export multiple scenarios out of OpenPHA, develop a bow tie, and then use the bow tie for evergreen management of that scenario, because we allow a easier to view representation of risk, and then also it allows you to drill down into those degradation mechanisms and degradation controls that are not going to be available in that simple LOPA tool. So, and this is just the beginning at Connexus. We're really liking this bow tie tool, and we see a lot of additional features and functionality in terms of real-time evergreen that we think are going to make this tool very valuable to us. So with that, I'm going to go ahead and open the floor up to any questions. Yes, Francois.
Yeah, good morning to you. It's afternoon for me.
Yes.
Go back to your slide with the level alarm I on the bow tie. The mathematic here is fine, but as we evaluate the probability of failure on demand on a safeguard on a yearly probability of failure, aren't we penalizing ourselves when we show more than once the same safeguard with the PFD?
Excellent.
So
question.
eventually, basically, if that level alarm I would show with the 10 different initial causes, it wouldn't do anything anymore.
Well, that is an excellent question. So kind of rephrasing the question, I'm showing level alarm 102 for cause number 1, level controller failure. I'm showing a level alarm 102 is something that I'm going to be concerned about with an operator failure of excessive transfer. And then the question is, well, the more I use this barrier, the more I'm dependent on it, meaning the more likely it is that the failure of that barrier is going to increase my level of risk. So what is the mathematical mechanism to address the fact that this level alarm isn't just showing up in one place, it's showing up in multiple places? Shouldn't that PFD decrease because it's being used in multiple different locations? And the answer is no. So the PFD of this equipment, so let's just say there's a collection of equipment that includes an alarm, and let's say it turns on a horn or a light, or a horn and a light. So that is the equipment that is LAH 102. The probability of failure of that equipment does not change depending on how frequently you challenge it. So whether you challenge it 100 times a year or once every 100 years, the probability of failure of that piece of equipment is only a function of its random hardware failure rate multiplied by the test interval divided by 2. So lambda times test interval over 2. That is the only thing that determines the probability of failure of that equipment set. So the number of initiating events don't do anything to change its PFD. Furthermore, when you look at each one of these initiating events, we made the assumption that they are independent of each other. They are not dependent. So failure of a level controller and the operator failure of overestimating is physically and functionally independent. So this row in the quantitative bow tie is completely independent from this row. Their frequencies will not affect each other. So how does the fact that I'm using this safeguard in multiple places affect the overall risk? Let's play a little bit of a numbers game. Let's say I had a different alarm, LAH103. So I've got one alarm associated with this human failure, and I've got a different alarm associated with the level controller. Now, if LAH103 is taken out of service, then this PFD becomes 1. Now, this frequency is 1 E minus 3, and this frequency remains 1 E minus 4, so the outcome is going to be 1.1 E minus 3 if I'm using separate devices to alarm. But if I use the same device to alarm and I take it out of service, now 102 has a probability of failure of 1 in both places. Now this frequency is 1 E minus 3, this frequency is 1 E minus 3, and now I have 2 E minus 3. So if you had independent alarms and you take one out of service, you get 1.1 E minus 3 as your risk. But if you have the same device and you take it out of service, 2 E minus 3 is now your risk. So the fact that they are the same device, that is known, that is considered in the bow tie diagram, but the fact that you're using the same device does not change its PFD, and because each cause is independent of each other cause, it doesn't change how you do this probability math. Is that clear? Does that make sense?
Yes, if you think the question was based, I agree the PFD doesn't change, but we base often our PFD on a failure per year basis.
Yeah.
And there's a flaw, isn't there a flaw in the maths that we do at that point when we use it many times?
Okay.
Yes, but I think we go maybe a bit too far for the training, but the testing interval gives us a probability of a failure over a year or 2 years, whatever. And we translate that into a PFD, which works great for one scenario at a time. But when we start adding scenarios, it doesn't. I worry that it doesn't reflect the performance of the safeguard.
But ultimately, those scenarios are all independent of each other. The independence of the scenarios is what allows you to not have to change the PFD, because they're independent of each other. And if they're not independent of each other, you can't use this at all. You need to go look at fault tree analysis that understands you're using the same safeguard for multiple different interdependent scenarios. So for the LOPA, for the quantitative bow tie, the independence of the initiating events is what allows you to use the same safeguard in as many scenarios as you want without changing the risk. The realization that the risk is actually higher is when you take that device out of service or you decrease the PFD of that device. It will dramatically increase the frequency of the outcome because the outcome is dependent on that one barrier in so many different scenarios. So yeah, I think we could go a little bit more into the details of dependency. What I'm going to recommend that you do is there's a recorded webinar on the Connexus website where I do a tank overfill that contains dependencies, a lot of dependencies in a fault tree analysis. And if you go to the Connexus website recorded webinars, I go into a lot more detail of how do you handle the fact that multiple scenarios have dependencies on each other. And that can only be done in a fault tree.
Hi, it's Alberto. I would like to ask a question regarding this topic of the franchise. I totally agree with the explanation from Ed, but if regarding this topic, talking about LOPA studies, if in a LOPA study I have several rows, each row means one scenario with its safeguards. In this case, in the end, I have to aggregate, I have to sum up all the risk reduction factors. No, this question is related with the one of Francois, because maybe he was asking not about the PFD, that I totally agree that is not going to change, but this final frequency, or in this case, in a LOPA study, the risk reduction factor, you have to aggregate, no, this final risk reduction factor.
Yes.
Of all the scenarios.
Right. So
the same that you have done with the frequency.
So in the quantitative bow tie, we are doing an aggregation. So, you know, we calculated, clear this up a little bit. So in order to get, okay, let me go to the end and work backwards. So I know that for this situation, my tolerable risk is 1e minus 4. For that consequence, my tolerable risk is 1e minus 4. I need to calculate a number to compare against that tolerable risk. And I calculated that as 2e minus 6. So how did I get there? Well, I use my PFD of my mitigative barrier, multiplied by the frequency of the loss of containment. But the frequency of the loss of containment was determined by adding the frequencies associated with all of the initiating causes, not just one at a time. So it's the summation is happening. If I let me get out of here so we can look at everything in one place. So the summation of all of the causes occurs here. So 5e minus 3 plus 5e minus 3 gives me 1e minus 2. And then when I want to know the frequency of any individual cause, I take the aggregated frequency of the hazard and multiply it by the probabilities of the barriers to get the frequency of the consequence, which I then compare against the target maximum event likelihood of the consequence. So there's some thought processes, some discussion needs to go into some versions of LOPA, many versions of LOPA actually, will only look at one consequence cause pair at a time. So if you are going to do that, then you would have to, if that is your company's policy, then you would have a bow tie for each cause and then spill out all the different consequences. But that's kind of counterintuitive and separate to the purpose of what we're trying to do when we're doing a quantitative bow tie, or any bow tie for that matter, which is to look at all the causes and all the consequences in one framework. Does that address the comment in question?
Yeah,
Okay.
totally. Yeah, I totally agree. I think that you have the risk is accumulative, so you have to take into account all the potential causes. But it was regarding the Francois question, because maybe it's true that if you're going to determine the C level or the PFD or the risk reduction factor, in that case, you are going to take into account all the potential causes. And in that case, maybe makes some sense this question regarding that the PFD is going to depend on the number of causes that it's covering. But that is done in a LOPA study when you aggregate all the risk reduction factors. But here, the PFD of a high level alarm, for instance, is 0.1. There's no question about it. That was more or less what I was trying to do. That's the motive behind my question.
Right, and ultimately, the PFD. So, kind of going in here. So the PFD of any one protection layer is not going to change depending on how many scenarios it's involved in. But if it fails, it will change the frequency of every scenario that it's involved with, and all of those scenarios will aggregate up. So it will, a failure of a protection layer that's used against multiple causes will aggregate very quickly, but its failure probability it's not a function of how many causes it's associated with. It's this risk aggregation number where that shows up, the fact that it's so critical because it's used in so many places. All right. Okay, so with that, I thank you all for taking the time to talk to me and to have a little bit of a discussion on bow tie diagrams. I hope everyone appreciated the discussion. And yeah, we'll be doing another webinar next month, and all of our webinars end up on our website. They also end up on YouTube. So thanks everyone for your time, and I will see you at the next one.
Thanks, everyone.